All right, ladies and gentlemen, I think I got everybody in attendance. As far as today goes, today we are bringing in one last step to our stoichiometry. So to our unit conversions. So we are bringing in our step of percent yield. So percent yield is percent yield. We are given an equation, basically percent yield, which if you did our notes, you would have this already, but percent yield tells us how well we did in our lab, how much we actually made when we did this in person versus how much we were supposed to make. So our actual yield, so we're looking at this equation, our actual yield is from a lab setting. Of some sort. So somebody did the lab, they massed out their final product, and this is how much they have. And so that's going to be our actual yield. Our theoretical yield is going to be the amount they are supposed to make. So how much were you supposed to make when you did the lab? Based on the numbers you started with. So that's when we're doing our stoichiometry to predict how much product we should have made versus how much you actually made when you did the lab. So it's just our actual divided by theoretical times 100, the same equation every single time. Never is going to change. Pretty simple equation. So what you guys are doing in these, I think there's only 4 problems. Yep, just the 4. So what you guys are doing in your 4 problems is you are first going to identify the limiting or excess reactant, because your theoretical yield is going to be the amount that you make by your limiting reactant. So you need to identify how much you'll make by your limiting reactant to figure out how much product you should make. And then you're going to compare that to how much it was actually made when the reaction happened. You're going to do that for 4 problems and then answer the questions, if there are any, after the reaction about what this reaction tells us, like this one right here. So then you'll answer what you think that percent yield is telling you about how this person did the lab. Is there any questions on what you need to be doing? All right. Then I don't want to make you guys stay if you guys don't want to go over practice problem together, because you guys should be able to do all this information. The only new thing is calculating percent yield, and that's very straightforward with actual and theoretical yield. Those should be pretty straightforward. So if you guys don't want to stay to go over an example problem together, you don't have to. You are good to go and just work on all 4 of these problems. If you want to stay, give me like a thumbs up or send me a message in the chat. Some way of me seeing that people want to stay and go over a problem, so we go over one together. All right. Got at least 1 thumbs up. So I'm assuming that everybody wants to go over a practice problem, since everybody stayed, which is awesome. So let's go ahead and take a look at this problem. It says the combustion of methane, which is CH4, produces carbon dioxide and water. Assuming that 32.084 grams of methane are burned with 13.45 grams of oxygen, what mass of CO2 is produced? So if we were figuring out what we're starting with and what we're going to, what information is important to us in this problem? Who could tell me one piece of information from the problem that we care about? The grams. Awesome. So we want, I'm assuming you mean all the grams. All right. So the grams are super important to us. It's telling us how much we're starting with. What else is going to be important to us? The balanced equation, awesome. And then there's one last thing that we care about. What do we care about? We know how much we're starting with. We have a balanced equation. What's the last thing we want to look at? Last thing we need to know in order to do this problem.
The mass of CO2.
The mass of CO2. So we want to know what we're trying to get to, what we're solving for. Perfect. So we have our starting masses. We have what we're trying to find. We have a balanced equation already. So if we were trying to write out what steps we wanted to take, we know that we're starting with grams of either methane or of oxygen. And we're trying to get 2 grams of CO2. Can we do that in one step, or do we need to figure out other steps in order to get there? And what would those other steps be? Can we go from grams to grams? We have to use our molar mass, so we use the molar mass of either methane or oxygen. So if we use the molar mass, what will we end up with if we used our molar mass? Will we end up with
Moles of methane and oxygen.
perfect. We end up with either moles of methane or moles of oxygen, depending on what we're starting with, depending on which one we're using. So we'd end up with moles of methane or oxygen. Can we go from moles of methane to grams of CO2, or from moles of oxygen to moles of CO2? Or is there another step we have to take? We got to use the mole ratio. Awesome. If we use the mole ratio, what are we going to get? What mole ratio do we need to use in order to get what? What units are we trying to figure out? I mean, moles of something. What are they going to be moles of?
Carbon dioxide.
Exactly. Since we're using the mole ratio, it has to be moles, and it's going to be moles of CO2, because that's what we're trying to get to, is grams of CO2. Now, our final step, can we make it from moles to grams of CO2?
Yes.
We can. And what do we have to use to get from moles to grams of CO2?
Molar mass.
The molar mass. Awesome. So we're going to use the molar mass over here. All right. So we have the molar mass, a mole ratio, and another molar mass. All right. So somebody tell me one of the molar masses we need to figure out. CH4. We need to find the molar mass of methane. So let's do that one first. All right, we have C and we have H. Who can tell me the molar mass of either of those two things?
Hydrogen is 1.01 times 4.
Perfect. We got to multiply by 4 since there are 4 H's. And what about carbon? What's the molar mass? 12.01. Awesome. If we add all that up, what do we get for the molar mass of CH4, of methane? 16.05, awesome. Grams per mole of CH4. All right. What's another molar mass that we need? We need at least two. We need
Oxygen,
more. Awesome, of oxygen. So what is the molar mass of one oxygen atom?
16 times 2.
16 times 2, awesome. Which means the molar mass of oxygen is what?
32.
Awesome. All right. What other conversion factors do we need for this problem? We need the mole ratio. Okay, so what mole ratios do we need? Who could tell me a mole ratio that we need?
One mole of methane and 1 mole of CO2.
All right. Do we need any other mole ratios or any other information from anything else? Any other conversion factors before we get started? All right. We need the moles of oxygen. All right. So the mole ratio for oxygen, how many moles of oxygen do we start with in that reaction? We start with 2 because I had 2 in front of oxygen. So we have 2 moles of oxygen equals the 1 mole of CO2. All right. So we have our mole ratios, we have our molar masses. Do we need anything else?
We need the molar mass of CO2.
We also need the molar mass of CO2. All right. We already have both of those, so I'm just going to rewrite them. 12.01 and 16 and times 2. What do we get for our molar mass of CO2? Awesome. 44.01 grams per mole of CO2. Perfect. All right. So now we have all our conversion factors for all the problems. Now we can set it up. So let's start with our methane. All right. We have 1, 2, 3 steps, which means we need 1, 2, 3 dividers, 3 breaks. All right. And then what do I put in my top left corner?
The 32.084 grams of methane.
Awesome. 32.084 grams of methane. All right. If I'm starting with grams of methane, what do I do next? Where's my next step? Where do I go? All right, so we're trying to get 2 grams of, so we're not going to go to grams of O2, careful. So that's a different problem. So this one is a different problem than the first one. So the grams of O2 is a separate problem than this one. Grams of O2 is going to be a different setup. So we'll do it a second time. That would be down here where we put the 13.45 grams of O2. But we're going to leave that part out for now. We're going to ignore that for now. We're only going to work with methane. And what units are we trying to get to? We're trying to go from methane to CO2. So what's my next step in going from methane to CO2?
You use the molar mass to get the moles of methane.
Awesome. We want to use the molar mass to get to moles of methane. So do I put my 16.05 grams on top or the bottom?
Bottom.
On the bottom, all right, which means we put 1 mole of CH4 on top, leaving it so our units of grams of CH4 have gone away. And now we're in moles of CH4. What do we do next? What are we going to do next? After we're in moles of CH4.
You use the mole ratio to get moles of CO2.
Exactly. We use the mole ratio to get to moles of CO2. So our mole ratio, we have 1 mole of CH4 to 1 mole of CO2. Do I put my 1 mole of CH4 on top or on the bottom?
Bottom.
On the bottom, we want those moles of CH4 to cancel, which means 1 mole of CO2 goes on top. That way our moles cancel out and we're left with moles of CO2. Once I'm in moles of CO2, what do I do next? We use our grams of CO2. Awesome, we're using that molar mass. Do I put the 44.01 grams of CO2 on top or on the bottom? Do I put the grams of CO2 on top or bottom? On the top, awesome. So 44.01 grams of CO2 on top because the 1 mole of CO2 goes on bottom, so they cancel out. Now all that's left to do is multiply everything on top. So we do the 32.084 times the 1 times the 1 times the 44.01, all divided by our 16.05 times 1 times 1. And this will give us our value for grams of CO2. And what do we get? All right. 87.976 grams of CO2. And that's 5 sig figs because our problem with methane started with 5 sig figs. So perfect. All right. So we're not done because we were told the mass of both starting things. So we're going to bring up our oxygen now, and we're going to do it a second time. So we're bringing up that 13.45 grams of oxygen. And we're doing it a second time. We're going to have those same 3 divisions. But now instead of methane, we're using oxygen. So what's my next step? Going from grams of oxygen to what? We're going to use the molar mass of oxygen. Awesome. Do I put my 32 grams on top or on the bottom? On the bottom. So this time the 32 grams of O2 for every 1 mole of O2. That way our grams of oxygen get canceled and we are in moles of oxygen. What's my next step? We use the mole ratio. Awesome. This time it's 2 moles of oxygen, make 1 mole of carbon dioxide. Do I put the 2 moles of oxygen on the top or the 2 moles of oxygen on the bottom? On the bottom again. Perfect. And that means the 1 mole of CO2 goes on top. So our moles of oxygen are canceling. And last but not least, what's my last step? We use the molar mass of CO2. Do I put my 44.01 grams of CO2 on the top or the bottom? On the top, the exact same as the previous part. If you notice, they look identical at the very end, which if they don't, that means that we are making a mistake in one way or another. And our last thing we are going to do is do our 13.45 times 1 times 1 times 44.01, all divided by our 32 times 2 times 1. And what is our answer for this problem? (9.250 grams of CO2. This one's got 4 sig figs because 13.45 grams of O2 has 4 sig figs. So now our last step is to decide how much CO2 are we actually going to make? How much CO2 should we be making during this reaction? How much am I actually going to make when I do that reaction? Exactly. I'm making my 9.250 grams of CO2 because once I make that amount of carbon dioxide, I've used up all the oxygen present, which means no more reaction can happen because this right here is gone. Once I use up that 13.45 grams of oxygen, my oxygen's now gone, which means I can't react my methane with anything to create my carbon dioxide and water. So once I get to my 9.25 grams of CO2, I am done. That's all I can make. Now for the new part, that percent yield stuff. So we know that the percent yield equation, so percent yield, which it says it above, is our actual yield divided by our theoretical yield multiplied by 100. Who could tell me what my actual yield is and who can tell me what my theoretical yield is? I want to know both of those numbers. Somebody tell me one of them. All right, my actual yield I heard was 9.250 grams of CO2. Okay, so then what's my theoretical yield? If that's my actual, what's my theoretical? All right, I heard 87.926 grams of CO2. How does everybody feel about those two numbers? Everybody agree? Everybody love them? Any qualms? Everybody's happy? All right. This number right here, this 87.926 grams, not useful in any way to this problem anymore. So that number we're going to get rid of altogether. That number's not helping us. Nothing about that number helps in any way, shape, or form. So now we have this 9.250 grams of CO2. Now that one Is that something we did in a lab or is that something we did on paper? Is that something we measured on a lab or is that something we're measuring on paper? On paper. So if it's on paper, that means we're doing, like, we're coming up with a theory. This is how much we're supposed to have. So this 9.250 is actually our theoretical yield. That's how much we're supposed to be making. But how much did we actually make during this reaction? We just made this 9 grams, exactly. So we actually made 9 grams. We were supposed to make 9.25 grams. So there is a difference. So we're going to figure out how much, what percentage of our mass we actually made. So we're going to take our percent yield equals that 9 grams of CO2 divided by our 9.250 grams of CO2. And we're going to multiply our division times 100 to give us a percentage. So what percent did we actually make? What percent did we make of this product? All right, I got 97.30%. Everybody good with that number? I like it. All right. One thing I do want to say is because of our actual yield now, our significant figure does change. So this one's actually just going to have 3 sig figs, but this is perfect. Other than that, it's awesome, wonderful, amazing. So we have our percent yield. Woo! All right. Now let's just talk real quick. That percent yield is 97.3% of what we were supposed to make, we did make. Do we think that is a good percent yield? If you were doing this lab and you came up with that amount of CO2 at the end, do you think that would be considered a good lab? Did you do well? Yes, exactly. You did great. 97.3. That is a wonderful percent yield. Now, what if it was like 37.9% yield? Is that a good lab? No, probably not. You did a lot wrong. There were a lot of mistakes going on. And somehow you did not make enough product. Somehow we lost something. Either we're spilling it all over the place, we didn't actually mass it out correctly, something went wrong. What if it was like 130% yield? Is that good? I feel like that's got to be good, right? All right, why do we think it's bad? We made 130%. I made so much more than I was supposed to. All right, let me ask this question. How many of you watched like that TikTok or that video about like the guy saying like, oh, you put in $20, no, I put in $20, and then I take this and give you $30? Have you guys seen that video? Am I crazy? Potentially. No, well, that's not helpful then. So instead, let's just think about this. If during a reaction, the most you can make is this 9.25 grams of CO2, that's the most you can make. Because once you make that, our oxygen's gone, the reaction can't happen anymore. Now we're saying that you made like 12 grams of CO2. That means that you probably didn't make 12 grams of CO2. you just have an error in your lab somewhere where you are massing out some of the reactants still. So some of our gas that you created, some of that mass is our methane that you're keeping there with the CO2. It's somewhere else. It's some other form of a reactant or a different product, something you did not finish completely, making it so you have more than you should. So it's not that you actually have more than you should. You just made some other error somewhere else, causing it to look like you made more. Does that make sense? All right. Does anybody have any questions on this worksheet and what you're doing for the other 3 problems? All right, ladies and gentlemen, then have a wonderful rest of your day. I'll see you